Oh, it's our great pleasure to have you, Karen, talking about health dynamics. We're very much looking forward to the next 1.5 hours. The floor is all yours.
Great, thanks. Like I said, I'm Karen Kopecky. I work at the Federal Reserve Bank of Atlanta. You know, the views, everything I say in this presentation has nothing to do with the bank. And I'm going to talk about, excuse me, measuring and estimating models of health dynamics, measuring health and estimating models of health dynamics over the life cycle. And this presentation is primarily based on recent work I did in a paper called The Evolution of Health Over the Life Cycle, which is forthcoming in red. And it's also somewhat related to another paper on the impact of health inequality on lifetime earnings inequality, which I'm going to talk about more at the conference tomorrow. And I'm sorry I can't be there in person. I do hope that if you're interested beyond what happens today, or you have further questions, that you reach out to me, and I'd be happy to, have email exchanges with any of you, or even, meet with you over Zoom to chat further if that's something you'd be interested in. Okay, so one of the challenges of studying health dynamics over the life cycle is that it's not exactly clear what health is and how we measure it, right? If you kind of ask everybody in the room what is health, you might get a lot of different answers. And so we can think that maybe at best what we observe in the data, in data sets, is some sort of noisy and incomplete and somewhat diverse set of signals that are informative about some true underlying health process. So things like self-assessed measures of health, like they ask people, how do you rate your health? Excellent, very good, good, fair, poor. Self-assessed kind of measures of impacts of health on activities. Like, are you able to walk across a room without difficulty? And then there's some that probably more objective measures of health, such as questions about, has you ever been diagnosed by a doctor with, with a particular medical disorder like diabetes, and also do you have, do you have difficulty, dressing yourself without assistance? Like, do you require assistance to eat or dress or go shopping, something like that. So this paper is really thinking about how we can use these various kind of signals about health to create a informative measure of health that's also tractable for, and here I'm particularly thinking about tractable in terms of embedding into a complex structural model, right? And so we may just think, well, we have 30 measures of health, we'll just include all 30 of them in the model, but often that's not really a feasible way to think about health as like a 30-dimensional object when we're embedding it into a model with a lot of other state variables. So we're going to think about how can we use these signals to create an informative, tractable measure of health, and then, given a measure of health based on these signals, and what are some basic facts about life cycle health dynamics, and how can we model them? Okay, so what am I going to do? I'm going to present a simple unitary measure of health that's going to aggregate information from a wide range of health indicators. And this is called the frailty index. And I'll talk in detail about this and why I think that this is an attractive way to measure health and aggregate the information in all these different indicators. And then I'm going to talk about 4 stylized facts about life cycle health dynamics that emerge when you kind of look at the dynamics based on this measure. And then I'll talk quite a bit about robustness. So then I'm going to compare this measure to other measures. Particularly, I'll do a comparison with self-reported health status, and the reason I focus on self-reported health status is that, in economics, still, this is the most commonly used measure of health in when people are modeling health dynamics in structural models. So people do other things, but if you kind of just look at the mode, this is the most common thing that people do. And so so we'll do a comparison to see how different is this frailty index from self-reported health And then I'll also talk about additional robustness of these 4 stylized facts to alternative ways of constructing the frailty index. And then finally, what I'm going to do is I'm going to talk about what is a model of health dynamics over the life cycle that's going to be consistent with these 4 stylized facts. And it's going to be a stochastic model. And then I'm going to talk about how you can estimate that model. And what's going to be crucial there is that when you want to estimate a life cycle, a process for life cycle health dynamics, it's really crucial to control for selection due to mortality, because perhaps not surprisingly, poor health and mortality are highly correlated. And so especially as you get into like looking at older individuals, the sample is highly selected towards people who, are still alive and are healthier as a result. Okay, so let's talk about what the frailty index is. So this is a very simple way to aggregate information from several health variables, which I think one of the things that's attractive about it, it's just the cumulative sum of all adverse health events. So you can think of these as deficits. So you think about each one of these variables, if it's kind of, the answer, like, yes, I have difficulty walking across the room, or yes, I was diagnosed with heart disease, then that would be considered a deficit. So you just add up the total number of deficits the individual has as a fraction of all the deficit variables you observe, and we normalize it between 0 and 1. So it's just a fraction of all the deficit variables that you observe. What fraction does this individual have at this point in time? And that's the value of their frailty at that moment in time. And this notion of frailty index comes from the gerontology literature. And in gerontology, it's been widely used to study health, and it's been shown to be robust to the exact set of deficits you use, as long as you use a large enough number. They've also shown that it's a better predictor of mortality than age. And so the types of deficits that we're going to use to construct the frailty index are these deficits that say whether or not you have difficulties with activities of daily living, like eating, dressing, using the phone, these diagnosis variables. So these are questions about, like I said, has a doctor ever diagnosed you with a particular disorder, like heart disease, psychological problems, loss of memory? And then we have some body measurements, like if you have a BMI over 30. Okay. And I think there are several advantages to using this, and I'm going to touch on some of this more as we go through the talk, but this is sort of my long list of why I really think that this is a nice way to measure health, particularly, like I said, for a measure that for studying the impacts of health on, on economic variables in like a large structural model. And the first one is that this is an objective measure of health, which is really, I think, where we want to start if we want to think about like studying health contingent policies. I mean, most policies, like think about the Social Security Disability Insurance Program in the US, eligibility for that program is not based on your own views about your personal views about what your health is. They're based on, some objective measure of health, or, some objective information about your actual health status. And there's concerns with subjective measures that, concerns like things like justification bias, right? If I'm trying to get on Social Security disability, or I'm on Social Security disability, there's some evidence I'm more likely to just say, yes, I'm in poor health. So it seems like as a starting point for studying health contingent policies, we want to use an objective measure. As I already mentioned, this measure is very easy to construct, and it's univariate, so it's tractable for embedding into structural models with lots of other state variables. It's highly predictive of health-related outcomes. This is something I'm going to show you. So it's highly, it actually performs better than self-reported health status at predicting pretty much all of these outcomes that you would hope it would predict well, like mortality, nursing home entry, DI recipiency, medical expenses. And I think we also even look at retirement. It also, I'd say it's better than self-reported health at predicting the decline in health with age. Maybe a less biased way to say that is that with age than self-reported health status. And which seems to indicate that people tend to readjust the reference point when they're reporting their health using when they self-report their health. So essentially, like, as people age, perhaps what they do is, they say, well, yeah, I have a lot of health problems, but, I'm in my 70s and, I'm still able to, walk down the stairs. My neighbor is, struggling to even, walk down the stairs. So I think I'm in excellent health, and they report excellent health. And because of this kind of renormalization of the reference point as they age, you don't see as rapid a decline in health with age when you look at self-reported health compared to frailty, which is a more objective measure. It measures health on a finer scale, or on a fine scale in general, also a finer scale than self-reported health. And this is important because, as you'll see today, and if you see my talk tomorrow, all of the impacts of health really kick in the upper tail of the health distribution. So it's not really until you get up into pretty, it's not until you're already in pretty poor health where additional deteriorations of health seem to start to matter for things like whether or not you're going to work, whether you're going to go on DI, whether you're going to go into a nursing home, whether or not you're going to die. And so really, we need a fine enough measure of health that allows us to, see the variation in the tail, because that's kind of where all the interesting action is for most of these things that we'd be interested in. Then 6, it's a cardinal measure of health, and it can be treated as a continuous variable. And this is really nice because it means we can estimate like marginal effects, and we can also have a notion of the severity. When your frailty changes, the change is actually, going from 0.3 to 0.4 in the frailty index, versus 0.3 to 0.5, we can actually say something about, the 0.3 to 0.5 is a more severe change than 0.3 to 0.4. We really don't have any good sense of what is the severity of the change when people go from excellent to very good to fair to poor. Like, is it an equal decline in health with every kind of deterioration of self-reported health, or unequal? We really don't have any good way of getting at that. And then finally, what's really also very nice about this measure of health is it's extremely robust. It can be calculated in multiple data sets, and it's extremely robust across these data sets. And this is something we explore in on, I think, over 100-page appendix now to this red paper, where we show that, everything we do, I'm going to show you stuff from all 3 data sets, but everything we do in each of these data sets is very robust to what you would find if you looked at them, to the extent you can look at them in the other data sets. And this is, again, also useful if you want to embed health into a structural model, to look at other economic outcomes. You often want to exploit multiple data sets, right? Like, for example, PSID is great at looking at like earnings dynamics for younger people. But if you're interested in like nursing home risk or mortality, you really want to look at HRS. If you're interested, and this is very US focused, but that's because both these projects were focused on US data. But then, MAPS, like if you want to look at things like impact of health on total medical expenditures, you would have to look at MAPS, because you're not going to see total medical expenditures, including what like insurance pays in PSID or HRS. So it's really nice that you can kind of crosswalk this frailty index across these different data sets, and kind of exploit the relative comparative advantages of each of these data sets when you study, impacts of health.
So
okay.
Point, just ask a couple of questions that have come up. Now my screen went off, but I think, it's back. So John is interested in whether you would want to weight the conditions instead of simply summing. So thinking of some cancers which might have a much stronger impact than other conditions on your list. And Feder is asking, which was also on my mind, whether the total number of health deficits is fixed across data sets, and whether the frailty index then changes with how many data variables you use to construct it. So, but I guess you've just more or less answered that question, and we should postpone it up to the point where you compare the data sets. That's also what I was thinking, since the PSID and HRS will certainly be very different, whether you end up with very similar indices in the end.
Yeah, so answering first the first question about the weights. So essentially this index that I'm talking about now, the frailty index, is equally weighting each deficit, right? It's equal weighting. And we do a comparison to alternative weighting methods. I'm going to talk about that. So if you wait, I'll show you. I mean, but the big picture message that comes out of that is that, you know, qualitatively, the main features of health dynamics don't depend on the weighting, or at least doesn't depend on the different weighting schemes that we look at. There are some kind of quantitative differences, but they're, you know, relatively small. So I'll show that out. So I'll look at, we're going to look, and also another weighting scheme, which is kind of based on maximizing ability to predict subjective measures. And so I'll show you what happens when we do that. In terms of the number of deficits, yeah, the number of deficits varies across the data sets. And like I said, in the gerontology literature, they already argued that if you have at least like 23 deficits, then, you know, the frailty index is robust to the exact number of deficits you have and the exact type of deficits you have. And that's consistent with what we see as well. So we, like I said, if you're interested, go on my webpage, find the red paper and find the appendix as well, because most of the comparison across data sets is in the appendix. And we compare on everything you could imagine, you know, kind of the dynamics of health of this frailty variable across these three data sets, which do use both a different number of deficit variables and slightly different set of deficit variables. I mean, there's a lot of overlap, but they're slightly different. And what's actually maybe quite surprising is that our frailty index is more consistent across data sets than self-reported health. There's larger variation in the self-reported health variable. So yeah, so it seems that it's incredibly robust. Okay, so let's talk about the facts. And so I'm going to also use MAPSIM HRS, but a lot of the stuff is based on PSID, and the PSID is 2003 to 2017 PSID data. Prior to 2003 wave, it's actually not so easy to construct a frailty index because there's many of the deficit questions were not asked in the earlier waves. So that's sort of unfortunate, but we do have, you know, still 14 years of, you know, time series wise of PSID data where we can construct a frailty index. And we look at household heads and spouses 25 to 94. There's 28 deficits in PSID. For the baseline frailty index, we don't include any subjective measures of health. So there are some additional subjective measures, self-reported health status in particular, and some other subjective questions that we're not going to include in the baseline measure. This is because we wanted our frailty index to be objective. I mean, again, at the end of the day, all these questions are still self-reports. So, you know, I mean, but what I mean by objective is that they're based on much more narrowly defined and specific questions. And like the diagnoses variables are literally asking the respondent, have you been diagnosed by a medical doctor? So it's not like, do you think you have diabetes? It's, have you been diagnosed by a medical doctor? So they're much more objective, I think, than, you know, like how would you rate your health status on you know, a scale. And in the robustness, I'll talk about what happens if you want to add self-reported health status to the frailty index. It doesn't actually change things that much at all. And okay, so stylized fact one, frailty increases with age, probably is not surprising. It decreases with education. You can see the mean by education, level of education, and it's slightly higher for women than men. One thing that we consistently see is that the differences by education are much bigger than the differences by gender. And that's true kind of looking also within each age group. The other thing that you can see is that the increase in frailty with age is larger for the more educated group, the college grads, than like the less than high school and high school grads. This, as you'll see later, is actually due to mortality. because these guys are less educated, by the time you get into the older ages, the highly frail people have died. And so you don't see, so as a result, you don't see as much of an increase in frailty for these less educated individuals than these more educated individuals. Okay. Stylized fact 2, the dispersion, the variance in frailty is increasing in age. And again, this is true overall. It's true within each of these subgroups that we just talked about. The other thing that you see consistently is that there's a significant decline in dispersion with education. So there's more variation in frailty, even controlling for age among less educated people than more educated people. You also see slightly more dispersion for women than men. Okay, stylized fact 3, cross-sectional dispersion of frailty is right skewed, both overall and by age. And this is true. So this is the overall, this is for the whole sample. This is the cross-sectional distribution. So you can see, the long, thin right tail. These are box plots by age. And, there's really 2 reasons that the distribution is highly skewed. One is that there's a mass of individuals with 0 frailty. This is actually 24% of the sample for the 25 to 34-year-old age group, and it declines to less than 1% for the 85+ group. But in addition to having kind of this, this mass at 0, there's a long, thin right tail of, highly frail individuals. And you see this long, thin right tail at all ages. Okay, 4th fact, frailty is highly persistent. So these are 2-year transition probabilities for 2 different age groups. There's a 3rd one, the 75+ group is in the paper, but it's just a lot of numbers, so I didn't put it here.
Does the PSID follow people into nursing homes?
I think in the PSID you don't see people in nursing homes, no, but you can see that in HRS, and that doesn't dramatically change. I mean, for these 2 age groups, that's not going to have an important impact on these numbers. But for the 75+ group, I mean, in general, for 75+ group, I mean, HRS is going to be a much larger and less selected sample, exactly. Partly because, you're going to see the nursing home population, and you just have more 75+ people in the HRS than you do in the PSID. Yes. So these are the 2-year transition rates. So you can see that, the probability of staying in the same quintile is high, sorry.
One more question. Like many of the questions are like they try to screen whether you have a very bad health, and so I was wondering whether you're just picking up people that are very sick, and you end up ignoring all the people who are not very well, that have like a moderate health. And that's why when we look at the previous graph, the previous distribution, we see many people that they look okay.
So saying that
What extent?
maybe we're not capturing health variation among the healthier people.
Yeah, that you're just capturing the extreme of the distribution, given the question that you're using. I mean, at the end of the day, you're using like a screening scale, like, I don't know, like, that's my question.
Well, I would say that these facts, you also see them with self-reported health status. So these facts are robust. If you do this with self-reported health status, instead you get the same, these 4 stylized facts also hold. So in that sense, they're not unique to the frailty index itself. They're also robust to, the different weighting schemes. But, of course, again, we don't observe true underlying health. So, there could be, it could be that the way that these surveys are designed, there's not really good information about variation in health among the healthy. The other thing I would just say, though, is that in some sense, maybe we don't care as much because, like I said before, when you kind of look at where the impacts of health are, they're really in the tail. So maybe there are some particular types of questions where we would care a lot about, that I'm fairly healthy, but now I have some small change in my health. But I have, you know, it's less clear that I mean, something to think about, but it's less clear that that type of variation matters. Yeah, but at least for all the measures that we look at here, you know, these facts hold the distribution is highly skewed.
All right, so there's plenty of other questions coming in, but I would take the liberty and try to postpone them a bit, so you get along a little bit, and then maybe let's see what's left over, maybe in half an hour or so. Yep. So that's both questions in here and that were on Zulip.
Okay. Okay, so yes, fine, let's keep going. So like I said, it's highly persistent, and I think that's pretty clear from these tables. I'm going to keep going. Okay, and I think I've made this pretty clear, but these are the stylized facts. Frailty increases with age, decreases with education, not so big differences by gender. Cross-sectional dispersion and frailty increases with age. The cross-sectional distribution is right skewed at all ages and overall, and frailty is highly persistent. And these results are robust to using these alternative data sets. So let's now talk about how this compares to how frailty compares to self-reported health status. Okay, so self-reported health status, again, they ask people to self-report their health. Commonly, it's 5 groups like excellent, very good, good, fair, poor. And I already hit on a lot of the concerns. It's a subjective measure of health. There's evidence in the medical literature that there's reporting biases by age, gender, education, and race. There's concerns about justification bias. Again, that if you're not working, you might say, well, yeah, you know, I have back, you know, the reason I'm not working is I'm in bad health, so my health is poor. You might also say that because you're collecting benefits based on your, like you're collecting SSDI benefits, and you have some concern that if you don't report poor health, that, you know, somebody could notice that and you could lose your benefits. So justification bias is definitely more of a concern here. Also, because it's just it's just based on one survey variable, whereas frailty is based on several variables. It lacks cardinality, and it's a relatively coarse measure of health, at least compared to frailty. So despite these concerns, as I already said, qualitatively, it implies very similar health dynamics, and it's highly correlated with frailty. Quantitatively, we do see some important differences. And so here's what I was saying before about the fact that as people age, we see a more deterioration of health when health is measured by frailty compared to self-reported health status. So, you know, the colored areas in the background are the cross-sectional distributions of self-reported health status for these different age groups, right? So like at age 25 to 29, about 25% of people report excellent health. You know, this amount here, whatever this is, like 30% something report very good health, and so on. And you can see as people age, you know, a larger fraction of people are reporting poor health or fair health. And so to compare kind of the evolution of that distribution to the evolution of frailty, we group people into frailty bins based on cutoff points that are determined such that the distribution of people across these frailty bins at age 25 to 29 is the same as the distribution across these self-reported health groups at age 25 to 29. So, you know, we basically figure out what is the cutoff value of frailty such that, you know, everybody, such that we'll have 25% of people would be in the top frailty bin, the excellent health frailty bin. And then given that cutoff, we hold that cutoff value fixed now, and then we use that cutoff point to figure out where people should be, which bin people should be in terms of frailty as we move forward. And what you can see is when you do that, you get a much larger increase of people in the, you know, in the kind of the poor health, the poor frailty bins compared to the poor self-reported health bins. And these differences really start to rise around age 50. So you can see up until age 50, these lines are more or less tracking each other. And then starting around age 50, you see that health starts to deteriorate much more rapidly if measured by frailty than self-reported health status. So this is what exactly I was talking about, how there seems to be evidence that particularly as people get older, they start to become more optimistic, let's say, about their health relative to what objective measures are saying. Okay. the second difference we see is that there's significantly more variation in frailty than self-reported health status. And this is true at all ages. And so here are box plots of frailty within self-reported health status groups and by 10-year age groups. And so you can see that within each self-reported health status group, there's a lot of variation in frailty. And the amount of variation actually is larger as you get to the poorer health groups. And which again suggests that people who are in, poor health, some of them may be more optimistic about their health when they're reporting self-reported health status. It may also be that people in poor health, that self-reported health may be more informative about, may provide additional information about health for people who are in poor health. But essentially, you see lots of variation, even in excellent health of frailty, and even among younger groups, you see a lot of variation in frailty. Okay. And then here's the comparison on persistence. And so here you can see that not only is there more variation in frailty, but the frailty is, kind of maybe despite that, frailty is more persistent than self-reported health status. So again, we kind of use these frailty categories that we created here, and we look at two-year transition probabilities across frailty categories compared to self-reported health categories. And again, you see more persistence in frailty than self-reported health status. Okay, so we just saw that health is more persistent and deteriorates more rapidly with age when measured by frailty, and that there's substantial variation in frailty within each of these 5 self-reported health status categories. So given these findings, now I want to talk about how do self-reported health status and frailty compare in predicting health-related outcomes? Like, do these differences in the features of these 2 different measures of health matter for their ability to predict health-related outcomes? And as part of that, let's think about, is the variation in frailty within self-reported health categories that we just saw, is it actually informative? Does it provide additional information about health? Is it informed about predicting health outcomes? And in general, is there independent information about health in each of these measures? So does self-reported health status, have bring some additional information to the table? So to answer these questions, we're going to look at 5 health-related outcomes: medical expenses, DI recipiency, retirement, mortality, and nursing home entry. And we're going to regress each of these on a quadratic in lagged frailty, lagged self-reported health status, or both. And when we do that, we're going to add some controls. We're going to control for quadratic in age, gender, education, and marital status. Okay, so here's what we find. So this is looking at total medical expenditures in MEPS. And yes.
Can you just go back to the previous slide? So that's maybe a good point to jump in with a couple of questions. So one by Gabriella, who asks, to what extent your measure would be dependent on the availability of health insurance, especially to the extent that some of the questions might be, did a doctor ever tell you? So if I don't have health insurance, I will see a doctor much less often.
Well, I don't know. So first, I don't think that statement is completely true, in the sense that it is true that maybe people who are more likely to be uninsured are less likely to see a doctor, but the evidence in the literature is that that's not because of lack of insurance, but because of less education. Like, once less educated people go to see doctors less often, even when they have access to health insurance. And that's actually, but yeah, but given that, I mean, it actually is interesting to think about whether or not somehow the fact that people might see doctors less often might impact the measure of health. I have to think about that some more. I mean, most of these medical events are pretty big ones, right? Like, this frailty index not going to capture things like, oh, I caught the flu and I'm, like, kind of sick for a couple of weeks. I mean, these are pretty big medical events. Like, I have heart disease, I have diabetes, I have cancer. So in that sense, potentially there's going to be less concern about the fact that some people may have not been diagnosed. But I thought, I should think about it more with education. I think this definitely might be part of the reason that we see some kind of strange differences. If I have time, I'll show you at the end. For the less educated like the high school dropout group, like the high school dropout men, I mean, the data is so noisy and they seem to be, I don't know. They seem, I'm trying to remember which way it goes. I think that their differences relative to the non-high school women are bigger. And I don't know, I know at one point we were kind of wondering if this is like that these, men who drop out of high school perhaps are just, they just don't really take a lot of effort to invest in their health. They maybe don't go to the doctor, and so they just are uninformed about their true health status. But yeah, it's something to think about more. Like we could think about the kind of ability to predict things like mortality by education or gender, or we could also look at the insurance variable itself. Although my basic view from reading the literature is that it's not really directly about access to insurance.
I would have one on the persistence. So one of your conditions was, did you ever have heart disease? So to the extent you have several of these, then the persistence is built in a way, no? To the extent that you don't have measurement error.
Yes. Yes, and we actually in PSID we actually do correct variables. So we kind of correct for measurement error, that if people reported that they were diagnosed with heart disease and then in the next wave they say that they were not, we actually correct that. So we actually remove that type of measurement error where they've changed their view. And so yeah, this does build in some persistence. But not all of the deficit variables are permanent. So we have a kind of combination of some permanent variables and some non-permanent variables. And I guess the view is that these types of diagnoses, these are, do have sort of permanent effects on your frailty. Because again, these are big, like if you have, most of these conditions are conditions that you don't fully recover from, or, the fact that like if you have heart disease, usually now you're on, some type of drugs to manage it for the rest of your life. If you have diabetes, same thing. So yes, this stuff.
Yeah.
Slightly more persistence in frailty than in self-reported health status. But you can see that self-reported health status is also very persistent. But yeah.
Great, thanks.
Okay, so let's look at predictive power. I mean, and this is maybe the other test to think about, is this a reasonable measure of health? Is kind of, you'll see that while there are differences in predictive power, they're not enormous. So what you can see is that both measures, frailty and self-reported health, are predictive of future medical expenses. And so we do this in MAPS because we're looking at total medical expenses. Kind of comparing on the R-squareds, you see that frailty is somewhat more informative, right? And so this is what I was saying a moment ago, that, if you're concerned that frailty is some weird measure of health, I mean, if anything, it tends to outperform self-reported health consistently in predicting health-related outcomes. So this kind of makes me less concerned that we're doing something very bizarre by including deficit variables that never go back to zero. If you include both of them in the regression at the same time, you see that both of them have independent predictive power. So self-reported health and frailty are both statistically significant when you include them both in this regression. But the other thing you can kind of see is that, adding self-reported health to this regression doesn't increase the R-squared by that much. So self-reported health doesn't add that much additional information once you've already controlled for frailty. You can also see that by the fact that the coefficients on self-reported health are, quite a bit smaller when frailty is in the regression than when we just have self-reported health here alone. The other thing you see is that then we run regressions. So within each self-reported health status group, we regress medical expenses on the quadratic and frailty. And you can see that within each of these self-reported health status groups, frailty has predictive power in explaining medical expenses, even in the excellent health group. So, this kind of indicates that the variation in frailty that we see within self-reported health status groups is actually meaningful variation that's capturing some type of, meaningful variation in underlying health. similar results if you look at people under 45. And we do this because one concern that you might have is, this frailty index comes from gerontology. So in gerontology, the focus is on, the elderly. And so you may be concerned this is not a good way of measuring health of younger people, but we find that in fact, just looking at the younger population, it performs similarly well to just looking at older populations. So again, frailty performs better than self-reported health. Self-reported health adds additional information, but not a substantial amount. And, so even for young people under 45 in excellent health, within frailty is predictive of total medical expenses. Same thing for becoming a DI recipient. This again is people under 66, because if you're over 65, you're 65 or older, you go to Social Security retirement, you can't be on DI. And, we see again the same pattern. Frailty performs better than self-reported health. There's some additional information, perhaps a bit more in this case in self-reported health. We could talk about why that's true, that this could be like moral hazard. And there's some independent information in frailty, or there's information in the variation in frailty within self-reported health status groups. Same thing if you just look at people under 45 going onto DI, and same thing if you look at going at retirement, mortality, and nursing home entry. So these patterns are very robust across all of these different health-related outcomes. Okay, so to summarize on this comparison of frailty with self-reported health, they have qualitatively very similar health dynamics, but some important quantitative differences. When measured by frailty, health is more persistent and deteriorates more rapidly with age, and there's more variation in frailty than you can see when you look at just self-reported health status. And to answer the questions I posed earlier, how do self-reported health status and frailty compare in predicting health-related outcomes? Frailty tends to perform better, and yes, the variation in frailty within self-reported categories is informative about health. So this is not just additional noise. This seems to be, does seem to be additional information here. But both variables do have independent information about health. Okay, so let's talk about robustness to the construction. So I just said, that self-reported health status does seem to provide some additional information. So you may want to include it directly in the index. And so we're going to look at what happens if you construct the same baseline frailty index, but now also include self-reported health status. Then I'm going to talk about two other variants. I'm going to explain these right on this slide. So again, frailty with self-reported health, we're just going to add self-reported health status as a deficit variable. And it's going to be that if your self-reported health status is fair or poor, then it's counted as a deficit and it's 0 otherwise. For the FPC index, this stands for first principal component weighting. So we're going to, instead of doing equal weighting, we're going to use the first principal component to weight the deficits following a paper of Perturba, where he did something similar in I believe using HRS. So, first principal component, what is basically doing is it's choosing to weight to kind of maximize the overall variation or capture the maximum amount of the overall variation in the deficit variables. And then the third version we're going to look at is something called the SIO index. This stands for subjective instrumenting objective measures index. And here we're going to choose the weights to maximize the power in predicting subjective measures of health. This index is inspired by a recent paper of Blundell with Eric French and Britton, I think, is the third co-author, if I remember correctly. And the basic idea of how this works is we're going to first create a subjective measure of health that actually combines 3 different measures. This is following something that they did. They do it for completely different reasons. So they don't exactly construct this index. They're doing like IV regressions, but the index is inspired by their use of objective health measures to or subjective measures to kind of reduce the, or, you know, of instrumenting subjective measures with objective measures to remove biases in those subjective measures when they use them as measures of health. And so we basically take 3 subjective health measures: self-reported health status, a question about whether people think that health limits their daily activities and whether they think that health limits their ability to work. And we take the first principle component, you know, kind of weighted average of these 3, and that creates and use that to construct a left-hand side variable. And then we run this OLS regression of that left-hand side variable on our set of objective deficit variables. And that gives us an estimate of these gammas coefficients here. And then the SIO index is just a kind of weighted average of the deficit variables, where the weights now are these estimated coefficients. And then we just renormalize, you know, we renormalize the weights, so the weights sum to 1. So they're the estimated coefficients kind of divided by the sum of the coefficients, so that the weights are, you know, kind of between 0 and 1. Right, so this is an index that basically chooses the weights to maximize predictive power in predicting this subjective measure. Okay, so what do these different weighting schemes imply? Just looking at kind of how they place the weights already gives you a lot of information. I think you can already kind of tells you a lot about what we're going to see when we compare across them. So if you think about the original frailty, so I just kind of grouped deficit variables into 4 broad groups. The variables about, you know, do you have difficulties with activities of daily living, these diagnoses variables, mental health variables, and self-reported health status as a separate variable. And you can see, you know, frailty by construction puts 0 weight on self-reported health. And it's about 46% on ADLs, 46% on medical diagnosis, 7% on the mental health variables. If we add in self-reported health, I mean, it doesn't change things that much. Now we're putting, you know, 3% of weight on self-reported health, and everything else gets slightly adjusted. If we do first principle component puts a lot of weight on the activity of daily living variables, consistent with exactly what happens within Perturba's paper as well. And, you know, you see this in all 3 data sets. And it actually only puts 4% of weight on self-reported health. The SIO index also puts a lot of weight on these activities of daily living variables relative to the other variables. So you can see already that these 2 indices, the first principle component and SIO, are more similar to each other. And these 2 indices, frailty and frailty with self-reported health status, are more similar to each other. That said, the first principle component and SIO indices are not quite as similar as you might first think. And this is because the SIO index is actually puts substantial weight on just 2 of the ADLs. So FPC kind of puts relatively equal weight on the different ADL variables. SIO puts 44% of the total weight on you know, I have difficulty with heavy housework and difficulty walking. And my guess is that this is because, you know, this, you know, saying that you have that health limits your daily activities and your ability to work also means you say that you have difficulty with heavy housework and difficulty walking. So, you know, but like I said, this, you know, so we could experiment, for example, with not using these 2 and just using self-reported health. That's something we haven't done. And that's partly just because we created this index particularly following Blundell and others who have followed this literature of doing this subjective instrumenting objective in kind of a similar fashion. And we wanted, you know, that was something that, like, referees, for example, in particular, were interested in seeing how things compare. Okay, so okay, despite these very different weighting schemes, and, you know, the fact that SIO is putting a lot of weight on just 2 variables, all 3 variants are going to be consistent with the 4 stylized facts that I showed you before, and have similar power in predicting health-related outcomes. And I keep hitting on this about the 4 stylized facts, because one thing I just want to push here is, if you might not like the frailty index for whatever reason, but these facts are extremely robust to all these different measures of health. And this is just something basic. I think if you're writing down a model and embedding health dynamics into that model, and I think it's important that at a minimum, whatever way you're measuring health, that you at least make sure that that measure is consistent with these facts, or show that it, or explain why you're not doing that. Questions?
Yeah, so we have two more long-standing questions. Let me just pass you on to Jasmine.
Maybe I missed it, but you say you talk about this power in predicting health-related outcomes. How you measure this power? Is it only the R squared, or is it like, do you make out of sample testing?
No, it's the R squared. It's
No out of sample testing.
no, we don't do out of sample testing.
Great.
Is it the R squared with the adjusted R squared?
Is it the R squared?
It's the R squared, not the adjusted R squared. Although the two are, I mean, everything that holds with the R squared holds with the adjusted R squared. I can't hear her.
The more variables you have, the higher the R squared. But I guess you just add one, right? Yeah. But
We use the R squared because of differences in number of variables, but it doesn't, the R squared and our just R squareds are so similar in these regressions. And we did versions with and without holding the sample size fixed too, because the other thing that happens is you get some variation in sample size because of missing variables. We did both versions with kind of maximizing sample sizes and kind of using a fixed sample. And yeah, I mean, the results are robust to those alternatives, but we didn't do any out of sample testing on this.
This table you got is the wonderful occasion to ask another question that John had, namely to the extent that there's growing evidence that human capital has multiple dimensions. You might want to think about multiple dimensions to health as well, in particular physical and mental health. And this table seems to suggest to me that that might be a good idea if you have enough room available for two variables, I guess.
Yes, and you can you could definitely, and that's probably the reason I separated out mental health, because this is something that you might think is like relatively more important for younger people than for older people. Like when you think about why younger people are out of the labor market, maybe it's more about mental health, whereas why older people are in the labor market, maybe more about physical health. So yeah, you could definitely think about like a multi-dimensional measure of health and split these things out. And that's not something that we do here. And that's partly just because, like I said, I think there's some value to having a univariate measure of health and then just documenting these basic facts about health dynamics, because that, and that's why the reason we ended up writing this paper is that really this paper started out as, work we were doing for the other paper I'm going to present tomorrow. But then we just, we couldn't even find a paper in the literature that just kind of documents basic facts about health dynamics that over the life cycle, and that talks about just how to model those health dynamics in a simple way. And I just think there's some value to sort of creating a reference. I mean, I don't know, maybe people disagree with me, but I just feel like, this is my personal opinions about the literature. And I've been in this literature a while that, I've refereed a lot of papers in those especially the more macro health literature, is that there's no standards and people just do whatever they want. And that's not necessarily a bad thing. I mean, that generates innovation, except that it's very hard to compare across papers. It's very hard to tell if what people are doing is reasonable. And so at least it seems like it'd be nice to kind of, have some standards to say, okay, here's some basic facts that, your paper, even if you don't use this measure, your paper should be consistent with, and, and here's kind of a way to model health dynamics that's really robust, that's really been checked in the data. So if you're going to just do something ad hoc, maybe you should do this. That's what I think. Okay. So yeah, so here's kind of just showing that these facts are robust, which I've already said that, frailty increases with age, decreases with education, and is higher for men than women. Whether you use, regardless of which of these kind of variations on the construction of the index you use, you do see more rapid increases with age with the FPC and SIO index. And that's because they're putting a lot of weight on these ADL variables, activities of daily living variables. And these, are variables that, most people who, have difficulty, eating without assistance are old people, right? So by putting a lot of weight on these types of variables, what happens is you get healthier young people and more of an increase in frailty as people age. Cross-sectional dispersion and frailty is increasing in age with all 4 of these variations. For the same reason as you get a larger increase in the mean with the FPC and SIO, you get a larger increase in the variance, right? Because, it's kind of a relatively small fraction of very old people who are going to have a lot of these problems with activities of daily living. And so you're going to get a lot of variation among old people by putting a lot of weight on that small group and less variation among young people. Cross-sectional distribution of frailty is right skewed, both overall and by age. This is true for all 4 of these indices. I just show you the mean versus the median so you can get a quick sense of that. And FPC and SIO are more skewed, particularly at young ages, again, for the same reason that because we're putting a lot of weight on these ADL variables, which only affect a very, very small fraction of young people, we get, a distribution that's skewed much more towards healthier people, towards having a lot of very healthy people in the FPC and SIO index. And frailty is highly persistent with all 4 of these variations. And you can see that here, I just report probabilities of staying in the same quintile, moving up and down 1 quintile or more than 1 quintile across these 4 indices. And you can see that it's actually incredibly similar persistence, probably because of what we said before, that the persistence is really determined perhaps by, the persistence of these individual deficit variables, not so much by the weighting. Okay. And then here's the comparisons on predictive power. And here you can see for total medical expenses, just comparing R-squares. Like I said, we did this also with a fixed sample, and it doesn't change anything about the relative values. They're very similar in predictive power. And, in this case, you can see that, so this is self-reported health, this is frailty with self-reported health. You can see that these 2 are doing slightly better here and here as well. If you look at mortality and nursing home entry, you can see that frailty with self-reported health actually does the best here, but the differences are small, except that SIO is not very good at predicting mortality. Interestingly, it doesn't predict mortality well, but what it's really good at predicting, and perhaps the only thing that it kind of predicts better than the other variants, is nursing home entry. But again, that's perhaps not surprising because people who have difficulty walking, for example, are the people who are most likely to end up in a nursing home. But just to summarize, so all 3 variants imply qualitatively similar life cycle dynamics. We do see some quantitative differences. However, the differences in predicting health-related outcomes are pretty small. And it's not like one version of this index consistently outperforms the other, right? It's not like we do, first principle component, and then all of a sudden that just outperforms everything. I mean, you see variation and no standout index that dominates the other, no standout, variation that dominates the other. Okay. So given these findings, now we're going to go back to our original index and estimate a model of life cycle health dynamics in the last half hour here. Okay, so I'm going to present a stochastic model of life cycle health dynamics, and this is a model that's consistent with the 4 stylized facts that I presented. And to estimate this model, as I mentioned, what's crucial is to account for selection due to mortality, and I'm going to show you why that's crucial. Or just how crucial exactly that is. And so when we estimate the model, we're going to explicitly model mortality risk, and we're going to estimate the model via simulated method of moments. Okay, so let's first talk about what is exactly the model. So remember that we talked about the fact that there's a large fraction of people with zero frailty, and this fraction kind of declines with age. So this is what this looks like in the PSID sample. So about almost 30% of people have zero frailty at age 25, and then this thing declines, pretty consistently to essentially 0 for people 85 and above. So to capture this feature of the data, we're going to assume that the probability an individual's frailty is 0 follows a probit model, where the covariates are going to be a quadratic in age, education dummies for less than high school grad, and college grad, and a male gender dummy. The other assumption we're going to make is that, so basically, some people will start out with 0 frailty at age 25 in this model. And once frailty goes positive, we assume that it never goes back to 0. And the reason that we do this is that in the data, less than 1% of people who have positive frailty then go back to 0 frailty. So just to simplify things, we're just going to assume that once your frailty is positive, you don't go back. So then once frailty becomes positive, this is the structure. It's very similar to the type of stochastic process structure that is common in the earnings dynamics literature. But it turns out that this structure, as I'm going to show you, fits moments from the data extremely well once you control for mortality. If you don't control for mortality, it doesn't fit, as we learned through experimentation. So we're going to assume that log frailty is a sum of a deterministic component and a stochastic component. The deterministic component is going to be, frailty is going to depend on a quartic in age, education dummies, and a male gender dummy. The stochastic component has 3 components. The fixed effect is in the stochastic component, and we assume that that's normally distributed. And here's the variance. And then an AR1 shock, and the AR1 shock innovation is going to also be normally distributed, and a transitory shock, which also has a normally distributed, which is also normally distributed. Okay. So like I said, we're going to estimate via simulated methods of moments. So we're going to construct data moments, and then we're going to construct counterparts using artificial data that's generated by simulating the model. When we simulate the model, we're going to simulate both frailty and mortality for a sample of individuals with the same distribution across education and gender at age 25 to 26 as in the PSID sample. So we also need to model mortality dynamics. And to do that, we're going to assume that the probability an individual I, say, is dead at age j plus 1, given that he was alive at j, is given by a probit. And we're going to allow mortality to depend on a quadratic in age, a quadratic in frailty, education dummies, and gender dummy. Okay, so the mortality probit's estimated directly, and we estimate it in the HRS. Because like I said before, HRS, we observe a lot more death in HRS than we do in PSID, just because of the HRS is a sample, of older individuals, and it oversamples even the oldest of the old. So here's the results of that estimation. One thing that I thought was interesting that came out of this is that once you kind of control for, age and frailty and gender, education doesn't have a statistically significant effect on mortality. Because we know in the US, for example, that there's big differences in life expectancy by education, more than 5 years, but it seems that all of that variation is picked up by the differences in, frailty and these other variables when we run this regression. Okay, the 0 frailty probit. So we also going to estimate this thing directly, but using the PSID. And the reason we do it directly and not through the simulated method of moments is because mortality doesn't have a big impact on the fraction of people at 0 frailty by age in the data. And this is what this picture is showing. So, the blue line is kind of the estimated probit. And when we simulate the model, you can see that there's some impact on these fractions due to the selection due to mortality, but it's pretty small. And just because at younger ages, mortality effects are small. And then at older ages, the fraction of people with 0 is pretty small. So kind of in an absolute sense, there's just not a lot of people with 0 frailty. And so then this selection doesn't really impact this, these fractions. And then, I think not surprisingly, we get that the fraction at 0 increases in education. So more educated people are more likely to have 0 frailty, and it's lower for men than for women. Okay, so let's talk about the simulated method of moment estimation. So once we've done these two things, we basically have 12 parameters that we want to estimate. These are the parameters of the log frailty process for people with positive frailty. So these are the 8 coefficients in the deterministic component, and then the variances of the fixed effect, the transitory shock, and the innovation on the air one shock, and the persistence of the air one shock. And so we're going to construct target moments using the PSID, and then given values of theta, we can construct simulated moments by simulating and creating an artificial data set. And then we're going to find theta that minimizes the weighted sum of squared differences. And for the weighting matrix, we use a diagonal matrix of the inverse of the estimated variances of each moment. So this is a weighting matrix that puts more weight on moments in the data that are better measured because there's larger sample, basically.
So there's one question by John. So that's in the life cycle model, whether you want their covariates for healthcare insurance, other indicators of investment in health status, like the amount of exercise, eating habits, indicators of obesity, etc. So the idea would be to see how, quote unquote, endogenous frailty, how endogenous frailty is, and what fraction of its variance is accounted for by decisions.
Yeah, you could do that. We don't do that here, but you could try to regress frailty on exercise. And I mean, the thing we looked at it in the other paper, and I'll touch on briefly tomorrow, is whether or not earnings shocks impact frailty, and we don't find any evidence that they do, which is broadly consistent with the empirical literature. We haven't looked at these other types of things. I don't know if you could do it in the PSID. So I'd have to think about what data set you would be able to do it in, because I'm not sure I don't think we have information about like exercise in the PSID. Probably in the HRS, you could look at this, but it's something, I mean, it's something that's interesting to think about. I guess my goal here was more just to, if you want an exogenous, a process for health dynamics, like where you're just taking health dynamics as exogenous, then here's a way that you could estimate that process. But yeah, it's completely interesting to try to think about what drives these dynamics. And so that's something I've been thinking about quite a bit, actually. Particularly, it's really interesting, I think, that to think about the fact that, as I'll show you at the end, there's just substantial variation in health dynamics over the life cycle by education, but it doesn't seem to be related to access to health insurance or differences in earnings or earning changes in earnings by education. It seems to be, and this is, like I said, again, consistent, like Heckman has some recent work on this, and there's a large empirical, like Cutler and others have looked at this. It seems to have something to do with the fact that more educated people just make better health decisions. And so it'd be kind of interesting to try to dig into that further and really understand what that means. Like, is it about that they exercise more? Is it that they eat better food? But that it seems to be that they just make better health choices. I mean, right now, I think one of the interesting comparisons is just looking at what's going on in the US with the COVID vaccine. The people who are not vaccinated are disproportionately less educated. And it's not because they don't have access to the vaccine or can't afford it. It's available to them at essentially no cost. they just don't want to get vaccinated. And so that's a choice they're making, despite the fact that, I mean, if you look, any way you look at the data, it's pretty clear that vaccinating is a better health choice. I mean, I think minus maybe very select group of people who, whatever, you know, maybe are very specific in their health situation, like immune compromised or something. I mean, that's kind of but what's going on with the COVID vaccine is very consistent with what you kind of see in the data, which is that less educated people just seem to have worse health outcomes. And it seems to be about the way they manage their health, not about these other variables, these other economic variables. So yeah, I'd be very interested to dig into that further. I just haven't done that here, and I don't know. I'd have to look into what data set I could do that in.
So I do have a completely different question. How can you tell apart conceptually, but also empirically, the variance of the fixed effect and the innovations to the AR1? So to the extent, especially if I think of the HRS, I would think of the initial conditions as sort of the accumulation of health shocks over the life cycle in a way, but then thinking about, okay, which part of that is time constant over a long horizon? I find that
I'm gonna show you, we're gonna target the autocovariance profiles of the frailty residuals, and essentially the overall level of variation is going to pin down the variance of the fixed effect, and then the kind of relative increase in the variation of older people to younger people is what pins down the variance of the AR1 innovation. And I can try to show that if I have enough time. I mean, it's a little bit more subtle in this setup because we're doing simulated method of moments and there's mortality effects. But like if you were just ignoring mortality and estimating this thing directly, then you could do by people like in the earnings literature, like Storslet and Violante, and I actually have them on the slide. I can show you in a few slides if you want. Like if you kind of stare at the so essentially you can derive from the model. Where is it? You know, you can derive the kind of analytical counterpart to the autocovariance matrix, the autocovariance profile matrix, and then you can kind of stare at that. And if you stare at that, you can kind of see where the identification is coming from for each of these different variances, right? But essentially, that's still what's identifying these things. And yeah, I'll show you again in a second. Okay. So let's talk first about the deterministic component. So to identify the deterministic component parameters, we target mean log frailty by age for each education group and for men and for women. And this is what the raw data looks like. You can kind of see there's this convergence of frailty by education at older ages, which we also saw in the table I showed earlier. This is something that, you know, in theory, if there was no selection due to mortality, you know, the current model wouldn't be able to match because we're just, you know, putting, you know, these education dummies in, we don't interact them with age. But, you know, one thing that you'll kind of see, where's the, well, I guess I show it in a second. Anyway, you'll see when it comes up, so I forgot the order, that this is something we're actually going to be able to match because of the mortality effects. Okay, and then for the stochastic component parameters, we're going to target the age-specific autocovariance profiles of the log frailty residuals. And there's kind of several steps that go into constructing these things. So I'll just quickly, you know, first you kind of have to, you know, regress log frailty in the data on the deterministic covariates to obtain the residuals. We group the residuals into 2-year non-overlapping age groups. And then for each age group, we can calculate a variance and an autocovariance. So autocovariances are like the, you know, the covariance between, you know, the log frailty residual at age J, and then at, you know, like age J plus 1, and then age J plus 2 and age J plus 3, and that's going to create like a autocovariance profile for that age group. And then we, you know, we also cohort adjust these moments, and to do this, we regress them on individual, we regress the individual specific moments on cohort and age dummies, and then we remove the cohort effects, and then we rescale so that the overall level of variation is the same as what we had originally. And so here you can see, this is on the left is showing you the raw moments, and this is after we do the cohort adjustment. And here you can see, so yeah, here's where I have the equation. So you can see that the profile is very hump shaped, and the autocovariance profiles are declining pretty rapidly in the lag length, and that rate of decline is kind of increasing with age. And it's like for example, the persistence is really identified off of these features of the autocovariance profile, the shape, the amount of curvature of the variance profile and the rate of decline of the autocovariance profiles. And you can kind of see that from these equations. This is what I was talking about before. So if we just did GMM and we ignored selection due to mortality, then these are essentially the model counterparts to the data moments that I just showed you in the previous slide. And here you can see, so here you can first see what I was saying to Hans Martin before, that the overall variation is determined. So kind of the overall level of the variances and covariances pins down the variance of the fixed effect. This parameter here is really like the relative. So this parameter is going to control kind of how the relative rise to some level, which is impacted by, essentially in the long, as age increases, we converge to some level of overall variation relative to the initial, and that's kind of dictated by this parameter. And rho is really going to dictate the curvature, both of the variance profile and, like, for example, you can see here that if rho is greater than 1, the variances profile will be convex. If rho equals 1, variance profile will be increasing linearly with age. If rho is less than 1, then it's going to be concave. And also if rho is less than 1, then these autocovariance profiles are going to be declining. And so if you kind of go back here and stare at this, if you ignored mortality and just estimated this thing, right away, you can see from the shape of this autocovariance profile that you're going to find that these AR1 shocks are not very persistent, because to get this type of, concave feature of the data and these rapidly declining autocovariance profiles, you need low persistence of the AR1 innovation. And as I'll show you in a minute, you would, because you've ignored mortality, you would actually substantially understate the persistence of these shocks. Because it turns out that this shape is heavily driven also by mortality. Basically, the persistence decline. People who are highly frail, people whose frailty is very, very persistent, are very likely to die. And so a lot of this decline in what appears to be decline in persistence is actually selection effects of mortality on the sample. Okay, so given theta, we can simulate the model, like I said, and we do this starting at age 25 up to 94. We simulate the model on an annual frequency, even though the moments are biennial. That's because we observe people every 2 years, and PSID is biennial over this period. But we construct these 2-year moments using the artificial data exactly as we do in the PSID sample. And we're going to use a minimization routine to find theta that minimizes this weighted sum of the squared differences between the moments. Here's the results. So here you can see the fit of the deterministic component moments. And here's what I was saying before, that the model can match this convergence in frailty with age across education groups, even though, in theory, this wouldn't happen if you didn't have mortality. So this is because of mortality. And here you can see that the model matches the shape of the variance covariance matrix. So it gets both this hump, and it gets the fact that these autocovariance profiles are kind of, increasing. The rate of decline of them is increasing as you move up to higher ages. And here's the parameter estimates that we get. So, like I just said, we match these features of the data of this autocovariance matrix, even though, we have a very, very high persistence, right? So this type of persistence, as I'll show you in a moment, without mortality would give you a very different autocovariance profile. And you can also kind of do decompositions that we do in the paper. So given these estimates, we find that the shocks account for 30% of the variation in the stochastic, in the residual at age 25. So kind of this ex ante or fixed heterogeneity is an important source of variation at younger ages, and then its relative importance declines. And by age 65, 81% of the variation is driven by the shocks, right? And that's probably because I said the shock is highly persistent. They are one shock. We also look at whether or not the model, how the model does in kind of just comparing the cross-sectional distributions by age. And this gives us a sense of whether we're kind of missing something first order, like some higher order moments that, the model is failing to capture, but we find that the model actually does very nicely. And so if you're interested in the appendix, we report, these cross-sectional distributions for every single age group. I just show you 3 here. And you can see that the cross-sectional distributions in the model and the data look very similar. So like, there's not some other crazy kind of higher order feature of the data that the model's not capturing. And then here's looking at the effects of mortality that I was talking about. So then what we do is we can stimulate the model shutting down mortality. And if you do that, you get, the red lines here and the kind of red variance, covariance moments here. So you can see that the effects of mortality are large, especially at older ages. And it's really mortality, as I already was saying, that accounts for the hump shape and the decline in the autocovariance profiles with age. And so, what this basically means is that if you ignore mortality, you would end up underestimating the mean at older ages, the variance at older ages, and you would substantially underestimate the persistence of frailty. Okay, so the other thing that you can do is you can estimate these processes separately by gender and education. And I'll just show you some pictures to convince you that, like we've seen throughout this talk, the differences by gender are not that big. So you do see, for example, more variation in frailty by education for women than for men. This is related to what I was talking about before, that the less than high school men, I think, are kind of a weird group. And you see more overall variation in frailty for women. And by education, you see quite a bigger differences. The main pattern that arises by education is there's less overall variation. So there's less, the variation of the fixed effect goes down as education increases. And there's less persistence and frailty at higher levels of education. Which also I think makes sense. So despite concerns you might have about how persistence is determined, I mean, it seems to me, there seems to be some evidence that more educated people are sort of better able to recover from health shocks, which is kind of, I think, consistent with the other stuff I was saying about differences by education.
So how about the relation between frailty and mortality by gender? So if I remember the literature correctly, it basically says that women tend to have more conditions than men, but are more resilient. So that would suggest that the relation between frailty and mortality then would be quite different across genders.
Yes, and I think I don't know if you can see it from the mortality regressions, but yes, so exactly consistent with what you're saying, even after you control for frailty, men still are more likely to die than women. So there's something in that sense, you can say, yeah, there's something that about men relative to women that impacts mortality that's not captured by frailty. And so, when that's part of the reason why you may want to do these things separately for separate groups, right? So when we do these things separately, we run all of these regressions separately for men, women, or for, different education groups. But yeah, I don't have the numbers for the separate regressions in the slides. Yeah, and I'm completely agree with all the views that it's interesting to think about why these things are true. That's kind of just wasn't what the goal of exactly was in this paper. The goal was first to just document what are the facts and how can we capture them, and then, think, and then I think there's a lot of interesting work. Sorry, I'm not going to skip through these graphs that could be done to then think about, you know, why we see these differences we see. And in some sense, yeah, I think this is something that's lacking in the macro or in the health, well, yeah, in this more macro structural health literature in general, is that we don't really have a good understanding of what drives health dynamics and why we see these differences in the health dynamics by gender, by education. And some, you know, like the standard endogenous health models, like the Grossman model, are generally not consistent with a lot of, I think, some of the basic things we know about the relationship between health and some other variables. So yeah, I think there's definitely work to go into the next step to think about kind of how you would endogenize health dynamics. And that's something I'm interested in thinking about more. So anyway, let me just quickly show you that the differences by gender, like I said, you can kind of see comparing the moments that, you know, other than the fact that for women, you get this like kind of jump up in the autocovariance profiles, that this higher overall variation, you don't see big, and you see slightly bigger differences, like I said, across by education, and that you don't see dramatic differences here. The bigger differences come by education. So here's the high school dropouts. And you can already see that going from high school dropout to high school grad, you get very different shapes of the variance covariance moments. And college, you know, going from high school to college, you get a dramatic kind of decline in the variance and the rate at which it increases by age. And you can see the big jumps also in the fraction with 0. So you can see the big difference between the high school and the college in terms of the dynamics over the whole life cycle. Okay, and I'm pretty much out of time, so I'll just summarize to say that what I hope you take away from this presentation is that frailty is an attractive way to measure health, and I think it's particularly maybe useful for thinking about the economic implications of health in structural models. Using frailty, we saw some stylized facts about health dynamics over the life cycle that are extremely robust to different ways of measuring health, and that I hope anybody who's writing down a model of health dynamics would compare to the facts that come out of their own model. Also be interesting to compare to other measures of health if that's what you're using. And we estimated a stochastic process accounting for selection due to mortality. It's important to account for this selection because mortality bias is large, especially at older ages. So unless you're only modeling health dynamics for people like under 45 or 50, then it's really crucial that you take into account this mortality selection effect.
Excellent, thank you. So let's give Karen a big clap. So that's probably the most active audience and talk we had in 3 days now. So that is great. Let's see whether there's any other questions. And to the occasion of your talk, even Eric has arrived. She won't hear you unless you take the mic.
Can you hear me from here? No. You need to take the mic.
Eric, I was telling them how great your paper is.
No. So question about the transitory component of health. So we can think of that as being one of two things, just bad things sometimes happen to people and they're transitory. The other is this is somehow or another measurement error of some sort. And I was wondering if you had thought about trying to disentangle the two. It seems as though in a lot of these latent variable frameworks, you could almost do something to try and think about, well, if all the different measures are sort of the measurement errors in all the different measures are independent of one another. For example, you could probably back out what would be the underlying variance of measurement error in these underlying measures.
Yes, we haven't tried to do that, but I think you're right that we could try to do this. So how is this? So what's the way to do this? Like, is this
Yeah, so I think if you think about things, so like the Heckman machinery seems like it works well for all of this. If you think there's some underlying latent variable like health, and then you have lots of different measures and they're all independent, right? And you can kind of, by instrumenting them with each other, you can kind of back out what are all the signal to noise ratios for all the different measures. You kind of sum up all the measures and basically can grind out the overall variance. It's one of these things that I'm not totally sure it's even worth the effort, but it seems like it's feasible.
I mean, shouldn't just the fact that we're using multiple variables, if the measurement errors are independent,
Yeah,
shouldn't the fact that we're sort of already aggregating across multiple measures sort of reduce the impacts of measurement error in one particular variable?
absolutely. Absolutely.
Yeah, but I agree. I mean, we could try to dig it deeper into what is exactly this, to what extent, yeah, the transitory variation, the transitory shock variation is actual health variation versus measurement error. I mean, at least it'd be informative from the perspective of then when you go and embed this into a model, do you want this transitory shock there, or do you want it there with a much smaller variance or not? Because if it's all noise, if it's all measurement error, you probably, you don't even necessarily want to include it, or you don't want to include it in your, in your bigger structural model that you're not using to kind of study impacts of health dynamics on other outcomes. Yeah, so no, it's something to look at. And I mean, maybe the other way to just look at what's kind of driving it, like which subset of deficit variables are the key variables, right? Because the concern could be too that a lot of these variables don't fluctuate, because like I said, they go from 0 to 1, then they stay there. And so we could look at what fraction of variables are actually driving this, and try to think about just whether that makes sense or whether it looks like it's more noise. Right. Because the thing that's true with this measure, I mean, this is a measure of health that's not really, I think, very good at capturing lots of types of transitory health events, right? Like I said, it's not going to capture that you have the flu for 3 weeks. And so, but on the other hand, it should capture some stuff. Like if you break your leg and you're unable to walk, it might capture that. Although the other issue is, we're kind of taking snapshots of people's health every 2 years. So it's going to miss a lot of these shorter duration, like transitory health events are just going to be hard to pick up. So yeah, I think you're right. I think it's a good point that maybe just at least at a minimum, think more about what is this transitory variation in the data, and yeah, maybe we could decompose it. Thanks, Eric.
Any more questions? So I might have one more, even though I probably am over my budget, but since I have the mic, I might as well overdraw a little more. So your frailty index reminds me of the accumulation of deficits that I think also comes from the gerontology literature. There's a paper by Dalgard and Strulik a couple of years ago. I think the main conclusion of them is, and a couple of other papers, that basically the Grossman model in a way gets the functional form wrong by saying, okay, we need a lot of health investments at points where health is very good in order to maintain it at that level. And this accumulation of deficits model would say, look, I've already 7 of your frailty conditions, then getting numbers 8 to 11 is much more likely than getting numbers 0 to 3. Is that something that comes out of your data analysis as well?
Yes, I think, yeah, and I'm trying to remember this because I remember what you're saying, but I haven't thought about it super recently. Yeah, but it's exactly what you're saying. Something about like, yeah, the rate of, in the Grossman model, the rate of change of deficit, the rate at which health declines, like has the wrong, like health declines. Is it health declines too quickly when health is good or something?
I think so.
Yeah, exactly. It's the opposite of what you see in the data, and that's completely consistent with what we find as well. Yes. So yeah, that we don't talk about that in this paper, but you know, our frailty measure, yeah, Dalgaard and Strulick, I mean, they're using the same measure as well. They haven't done what we've done with it here, but you know, the things that they find are generally consistent with what we see in this data set as well. Yes, and this is what I was referring to about the Grossman model. And like I said, I haven't brushed up on exactly the details of this, but I was looking at this a while ago. And yeah, it was exactly like the Grossman model essentially implies the wrong rate of change of health, I think. Like health depreciation, the rate of health depreciation, yeah, should be big when health is poor, not big when health is well or something. Yeah, it's like opposite. And that's what I'm saying. Sorry, I can't be, the Grossman model though, I can go back and look at my notes on this. I wrote up some notes on this a while ago because it's something I've been thinking about, because the Grossman model is just a dangerous model to use unless you really know what you're doing. It's just taking the off-the-shelf Grossman model. It can't match basic features of health dynamics or life cycle. And it also, I think, assumes like a constant depreciation rate of health, whereas you need to put in, yeah, it's related to this problem that you and I were talking about, that because of this assumption it makes, you need this like age-specific depreciation to have even any hope of matching the data. But that age-specific depreciation is related to this more fundamental problem about the assumption about how investments in health, the rate of change of health with health investments. And yeah, this is, yeah, so I mean, this is why I keep saying that just, yeah, I think more work needs to be done here. And somebody, you know, we really need to just, like a paper needs to be almost written to say, you know, like an updated version of the Grossman model, or, you know, like user's guide to the Grossman model, and what that really does a careful mapping of kind of what's in the, you know, the data to the Grossman model, and says what the Grossman model is consistent with and what it's not consistent with, and what maybe we would want to change to make it more consistent. Yeah.
Excellent.
I view that as a next step to what I did here. So
I'm looking very much forward to that paper of yours in the not so distant future, but even more so to your presentation tomorrow, I guess, at the conference, or the day after tomorrow. I don't really.
Yeah, thanks. And one more thing I just say real quick, that the Dalgaard and Strulick work is very interesting. Like they're kind of doing that. They've done some of that already. And I think that that's valuable work. So
I like that a lot, but I always thought it needed to be done on microdata rather than their more macro-ish approach. So it's great to see your work here.
Yeah, exactly. So like I think there is a paper to be written that kind of meets in the middle between what they've done and what I've done here, and ties to the Grossman paper.
Listen to that, people. So, thanks for your talk again.